A compound pendulum consists of a uniform rod of mass m and length 2L attached to the rim of a disc of radius L and mass 2m, so that no overlap occurs and the center of the disc is along the line of the rods. It is free to rotate about a horizontal axis through the free end of the rod, perpendicular to the plane of the disc. Find its periodic time. I say part of the difficulty is using that variable description to actually make a diagram. Okay, so this diagram in question is a rod. I'll just draw the circle first. Circle here, center circle there, and then we have is a rod. That's it there. Okay, so the usual applies. We have a axis P. I'll put it in red. That's what we're really looking for, is that there. We have axis C, which is about its own axis, and then we have to find some weights out here. Where does it say the rod size? Mass M. Okay, so it's going down with mg. Okay, and what about C? How much is that going down with? 2mg. Okay, what I'll do at the very beginning is I'll just do, remember the h value, we're going to need it eventually. The plane of the disc, find the periodic time. So periodic time is 2 pi I over mgh, but h it refers to the distance of the center of gravity away from the axis we're talking about. Okay, so we'll do that first. So marking some lengths here. We'll go for that being L because it's the rod is of length 2L and the disc is of length L. So in a nutshell, it's the turning moments equal the turning moments of a combined system if I was to treat them as 3 mg together. Okay, so if I was to treat that as a random body, and this is the axis P, the center of gravity is a distance. The 3 mg would work a distance h from the fulcrum, that is P. So what we're going to do is this. We're going to say mgl, mg times L, plus 2 mg times 3L. Finally, equals 3 mgh. Cancel the m's, cancel the g's, and we get what is it, 7L equals h, h equals 3h, h equals 7 over 3L. Is that what you'd expect? 7 over 3 just over 2? It's sort of the middle point between the two center of gravities, isn't it? If you look at the center of gravity here, the center of gravity here, and I'm saying that my one is just over 2L, so my new center of gravity is located around here. It's about right, isn't it? It should be located in between the two center of gravities. It shouldn't be located outside the two center of gravities. So when that happens, you know you're roughly it's a tick in the box that you more than likely haven't gone wrong. Okay, so we're up 7 over 3L. Now, let's get rid of it. 7 over 3L. Now, h equals 7 over 3L. Okay, and what we're going to do now, we're going to have to determine the inertia of the system. Okay, let's start off with the rods. Inertia around P, guys. What do you think? Inertia around P? 4 over 3 ml squared, because it's rotating around its end. So a rod rotating around its end is always 4 over 3 ml squared. That's for a rod of length 2L and mass m. Basically textbook specifications there. So it's going to be 4 over 3 ml squared. Now we go on to the circle and we're going to do IC. how it rotates around its center. Okay, and how does it rotate around its center? A half mr squared. The formula is a half mr squared for a mass m, radius r. What do we have? Mass 2m, radius l. So it's going to be a half 2m times l squared, which is simply ml squared. Now, do you guys get the next part? What can anybody predict my next step? Prediction on the next step? Okay. So the whole point of this is that it's what's called parallel axis theorem, and what we have so far is that we have the rod rotating. If you just take the rod in isolation, I'm just going to shade the rod in red. If you take the rod in isolation, we have it spinning around this axis here. Okay, so just like that, up and around. Okay, that's just the rod in isolation. Now, when you're not talking about the rod, we're talking about so this is the IP axis here, and the full system's rotating around that. So from a sky point of view, it's here, and then all of a sudden it rotates and the full system ends up down here. Okay, so we now have this circle, and it's going through this point here. What you know is about those two axes? They're parallel. Therefore, we're going to use the parallel axis term. Okay, so parallel axis theorem is that IP equals the other parallel axis to it plus md squared, where d is the distance between the two axes. Okay, so we're going to say IP. We're still only speaking about the circle at the moment. Okay, nothing to do with the rod. And what we're going to say is that it's IC, which is our ml squared. And how far are they apart? The two the two axes? 3L. 2L here and 1L there. So we're talking 3L here. So m times 3L squared, 3L 2b squared, and that makes it 10 ml squared. I always do this. Somebody tell me what I did. Mass 2m, not of m. So this, where's the last one? The last one's good because I used 2m. This one, however, it was meant to be a 2m, not an m. So what we're going to get is 2m. So that makes it ml squared plus 18 ml squared, which would give me 19 ml squared. Everybody alright with that? Okay, what's my I total then? Or I system? So I system, the system's inertia about P is two numbers added together. It's this number of the circle on its own plus where are you? This number, add them together. Okay, so add 4 over 3 ml squared plus 19 ml squared, and what you should get is 61 over 3 ml squared. Now we're on to the periodic time. We've already figured out the h of the system, so T equals square root of I over 2 mgh, and T therefore equals your I, which is 61 over 3 ml squared, all divided by the square root of 2 mgh Now what did we say H was again? 7L over 3. Worked it out at the very beginning. Let's cancel stuff. Sorry. Yeah. I forgot the G, did I? The G is still there, yeah. The L. Which one? The trees will cancel, won't they? The L will cancel with that L. And what are we having? 61 over 14. Ah, one other mistake, guys. It's always the same mistake. What is it? I've done one thing. Again. It's not 2m though. It's 3m because of it's the entire system's 3m, guys. So please remember to put in your 3 here. So it'd be just rub this out for a second. That I keep telling you, that's the one place you'll just shut off, and that's the end of it. Okay. So what's that going to be? 61 over 6 then? Oh, sorry, the 2 there. That 2 shouldn't be there. It was 3mg, not 2mg. So there we go. So it's going to be 61, and that L cancels there. So it's going to be 61 all over 21. 61L over 21G. And that's your periodic time. There you go. Okay. Let's hope next time I remember the M business again. I'm just going to start highlighting the M's all the time. Okay, move on. Another one. Okay. Question 10. Bit easier than it looks. A uniform rod of length 2p and mass 3m has a mass m attached to it at a distance y from A. Prove that the moment of inertia of this system about a smooth horizontal axis through A is 4mp squared plus my squared. Now, okay, one thing that's confusing here is, see this A here? What they really mean is capital A. It refers to a point. Okay? So we're talking about AB. We're talking that AB has a big length. Okay? It's of length 2p. So we'll put its center of gravity in the middle, and we'll say that's P here, P here. It has a mass m attached a distance y from A. Y could be anywhere, couldn't it? The mass could be attached. This big 3m mass. Well, I can tell you one thing. It can't be over this side, so y is a positive value, and it can't be beyond B. Otherwise, they're not attached. So you're saying that y has a range or a domain of 0 to 2p. Has to be somewhere in that value range. Would you agree with that? Doesn't matter where we put it. It really doesn't matter. Okay? And what we're going to define that as is y. And it's 3mg. The other one is the center of gravity of our whoa. Oh yeah, sorry. The y is actually mg, isn't it? And the rod itself is 3mg. Okay? What does that mean for the entire system? It's 4mg. I'm going to highlight that there in the hope that I will remember this when push comes to shove. Okay? Now, prove that the moment of inertia of the system about a smooth horizontal axis through A. So A is going into the board and it's spinning the full system around. Are we happy enough with that? Okay. Smooth horizontal axis through A. That means it has to go through A. So perpendicular. And then is 4mp squared plus my squared. Okay. What is the moment of inertia of a rod about its endpoint? Rod about its endpoint, anybody? Forward 3 ml squared. What's the specifications for that? The specs, so to speak? 2L and m. What do we have? So 3m, and we have y, isn't it? Or what's it called? P, sorry, P. So 4mp squared. That is known as the rod. Okay. Oh, sorry. That's not IP. What's that called in this question? IA, because it's going through the axis there. IA. 4mp squared. Okay. What about the mass? The point mass. I want to find the point masses IA. Inertia around A. Any ideas? Usually md squared, and it's a mass m, which is correct, and d equals y, so my squared. Total inertia, guys, is adding the two of them together, and you can clearly see that the total inertia is this one plus this one, which gives me exactly what's up there. Everybody alright with that? Okay. The system oscillates in a vertical plane about A. If the length of the equivalent simple pendulum is 40 over root 33p, show that y is either 2 over 3p or 6 over 11p. Make a prediction on your end equation. Two answers. What are you looking for at the very end? A quadratic equation with p as the variable. If you aren't getting a quadratic equation with p as the variable, you're not on the right track. Okay, so we'll just get rid of this for a minute. Now, the language of the question leads me to believe that I'm going to have to use t equals 2 pi root L over G for the simple pendulum. That's just to find out, that's just to give me the answer. The simple pendulum is 4 over 33p. So that would mean 2 pi square root of 4, 40, 32g on the bottom, p on top. That's going to be my answer for my compound pendulum, because it's equivalent to the simple pendulum of this length. So the periodic time of my compound pendulum has to be that answer there. Therefore, I also write beside this is my compound pendulum formula. Okay, I am going to calculate the h value straight away. Tend to like to work on the h value. Now, okay, so what is the, how do we get the h value, guys? Anybody remember? It's the turning moments have to be the same. So they're all clockwise turning moments at the moment, aren't they? They're all causing this system to rotate this way here. So the turning moments of the system is going to be mg times y plus 3mg times p is equal to what, guys? Remember, we're treating this system up here as a pendulum rotating around A. It has a new center of gravity. Its new center of gravity, a distance h away. So it's going to be equal to 4mg times h. We got to isolate h. So call it, what's it going to be? All the mg's will cancel. So I'm just going to get y plus 3p all over 4 equal to my h value. Everybody alright with that? Now, alright, I have enough to work this. Let's continue. Okay. So See the way this is going to equal this over 2 pi. What's our I value again, guys? We had it from part 1. 4mp squared plus my squared. Oh, sorry guys, show that y is either this or this, so it's going to be a quadratic equation in y as opposed to a quadratic equation in p. Okay, looking at this here, and then what's the m value this time? M value? 4m as opposed to any other answer. G, and then the h value. Now, also this is difficult algebra. That's all it is. Nothing more, nothing less. Okay, let's. I'm inclined to square both sides. I'm sure the g's will disappear anyway, but we'll just write them down for a second. And then 4 cancels with 4. The m's cancel as well, don't they? And 4p squared plus y squared all over y plus 3p times g, and as predicted the g's can cancel. Now we're left with something like this. So look, it's just a matter of getting a quadratic equation now, so we'll just continue on. Cross multiply, and we get 40py plus 120p squared equals 33 times 4 is, what's that, 132 p squared plus 33 y squared. Okay, the 33 y squared, bring over the 40py minus 40py, and then what's the what part's after that? 120p squared plus 132 minus 120. Now they just factorize it right away like it's nothing, but realistically it's a minus b, isn't it? So a equals 33, b equals minus 40, c equals 12, minus b formula 40 plus or minus, wait a minute, I need p in my answer. Okay, the variables are the y's, everything else is a constant. Was it? Yeah, it's gonna be 6 and 2 in a 3-11 split. Yeah. I'll just finish off this way anyway. B squared is 1600 p squared minus 4ac. 4 times 33 times 12. Anybody? So will you write that down for me? 4 times 33 times 12. That's what I'm talking about. All over 66 2a, 66 on the bottom. So 40 plus or minus, that's going to be 16p squared, isn't it? Which means we could have got factors for it. All over, yeah, and that's still 40p. Just be careful of that. Minus 4p all over 66. So it's either 44p over 66, or what's the other one? 36p over 66. Your two answers in question are 6p over 11 or 2p over 3. There you go. Are we happy enough with that? Yeah. So what you have here is 11 part 1. Proof that the moment of inertia of a uniform square lamina of mass m inside 2L about an axis through its centre in the plane of the lamina is a third ml squared. Please refer to 14b, exercise 14b for that proof. Now, deduce that the moment of inertia of a lamina about an axis through its vertex perpendicular to the plane of the lamina. Am I missing part of the question? Am I missing part of the question there? Oh, sorry, deduce it, as in get the formula yourself. It's not a proof question, so yeah, we get that ourselves. 14D. Yeah, that's grand. Okay, so look, you have your lamina. It's a square lamina, isn't it? And what's the dimensions of the square lamina? Goes through its center point. And what are the dimensions again? 2L in any direction. Okay. What about the corner here, guys? Pick any corner you want. Okay, so any corner you want can be what you're looking for. Now, I want to get its moment of inertia. Okay. What's the problem with the one that you have in the tables? What's the problem when it comes to rectangular or square lamina? What is the problem with the one that's in the tables? The one that's in the tables is parallel to the plane of the board, or it flips like this as opposed to a spin like that. So what you're really looking at is this. Imagine that's a 3D picture of it, and that's I want the central axis going straight through, like so, and I want it to spin like this around the axis. Okay, that's what I want. When I go to the tables, that's not what I get. So when I go to the tables, what I get is I get planes like this. They're actually in the plane of the board. Okay, so we can call them XX and YY. Doesn't matter which way you do it. Call that XX. Call that YY. Okay, and we call this IC, or the C axis, because that point there is C. Okay, perpendicular to X and Y. Now, guess what theorem I'm going to use before the parallel? They're perpendicular. The green one is perpendicular to the two red ones, so I have to use perpendicular axis term. IXX, it's a textbook 1/3 ml squared, is it? 1/3 ml squared. IYY, well look, it's IYY also has L, sorry, IXX has L either side. IYY also has L both sides, which means it's also going to be a 1/3 ml squared. Okay, IZ, or we call it the Z axis, going through Z. IZ is IXX plus IYY, otherwise known as the perpendicular axis theorem. Okay, and what we get here is 2/3 ml squared. Are we happy with that? Now, are we looking for, is the whole point of this question that we get it through the center? Is the whole point of the question that we do that? No. The whole point of the question is that we get it through one of its corners. So, through one of its corners, you can see a blue axis I'm just after drawing here. What do the green axis and blue axis have in common? They're parallel. Hence, you're going to recruit your good old friend, the parallel axis term, where we'll call this corner P. IP equals IC plus MD squared. Okay? Where D represents the distance. This distance here, D. Anybody tell me how to calculate D? Huh? Pythagoras, and you have the two sides, so it's going to be L and L. D squared equals L squared plus L squared is 2L squared. D will equal root 2L. So D is root 2L, which means IP ends up to be IC. What's IC again? 203 ml squared, yeah. MD squared, we already have it there, don't we? 2 ml, 2 times, or sorry, m times 2l squared. Multiply them and add them, and we get IP is 8 over 3 ml squared. Everybody happy enough with that? Now, the next one is sort of what they love to do with leaving cert. They love to throw a couple of extra bodies on top of the body you already have. So, if you look at the next question, part 3. 4 thin uniform rods, each of length 2L and mass m, are attached to the sides of this square lamina. Show that the moments of inertia of the system about an axis through a vertex, any vertex, perpendicular to the common plane of the lamina and the rods is 16 ml squared. So, from a 3D point of view, loving the 3D, you have something like this, and what you're going to have is I'm going to pick this corner here as my P. It's the center C. Now we have a couple of rods, okay, so I'll denote the rods here in different colours if I can. Yeah, blue. We have the blue rods. We have the green rod. Oh, sorry, not green. Brown rod. You then have the this one, purple rod, or darker blue rod, and finally the yellow rod. Okay, so the 4 rods are in a square around the system. Everybody happy enough with that? Okay, now what's the good news? The system itself, alright? The whole answer for the total inertia, I total is basically inertia of the lamina. So the inertia of the lamina on its own in isolation, inertia of rod A and B, IA plus IB, and finally the inertia of rod C and rod D. That's our goal. Can anybody tell me what's good about the lamina? We've already done it, haven't we? It's 8 over 3 ml squared. Now, IA and IB. What's really convenient about IA and IB? The green axis we're talking about is the end point of both the blue rod A and the brown rod B. So that means that they both must obey 4 over 3 ml squared. Is that alright? 4 over 3 ml squared. And as I say, I'll just call this is the P, so they're both 4 over 3 ml squared plus 4 over 3 ml squared. Now, here's the hard part. Do you notice that rods C and D, they seem to have 0 contact with the axis P, yeah? Can I, class, think of a way to shift one axis to another axis? There's a rules, one of the rules. The parallel axis term. What we do have, however, although we don't have the moment of inertia on P, what we can do is we can draw the center points in of each rod. Each rod's weight acts through the center of gravity of the rods. We can then use the calculation of the moment of inertia through the center of the rods perpendicular to the plane. So for both of these, that that one there would be I equals, what's it, 1/3 ml squared. 1/3 ml squared. And what we're talking about is an axis. We're talking about is an axis going through the center of both of them. All I have to do then is, if I call that IC and ID as an example, all I have to say then is that the IP, using the parallel axis theorem, is IC or ID plus MD squared. What does the D stand for in this question? The distance from the C axis to P and the distance from the D axis to P. They're both going to be the same thing, aren't they? Because it's a square. Not always going to be a square, but in this time it is. So, P to C, L across 2L this direction. Pythagoras' theorem. Call this the distance D. D equals 2L squared plus L squared. D equals 5L squared. D squared equals 5L squared. D equals root 5 L. Everybody cool enough with that? Or D squared is 5L squared is what we need. So, both of these D squareds here, they're both going to be 5L squareds. Okay, what about the IC and ID? We had it earlier. They're about 1/3 ml squared because they're rotating through the central axis. Add them together and what do we get? What's each one singly? 16 over 3 ml squared. Okay, 16 over 3 ml squared. Anyhow, teacher thoughts. Now, this one here, guys, your 16 over 3 ml squared. There's two of them, so that's the IC and the ID are both 16 over 3 ml squared and 16 over 3 ml squared. Now that one's a bit of a mouthful, but what we can do next is just add them all together. Let's just save me the hassle of that, and we'll say the answer is 16 ml squared. Okay. Done. Okay. If this system were used as a compound pendulum, making small oscillations in the vertical plane about a horizontal axis through vertex perpendicular to the common plane, grass is green, etc. Like just normal pendulum, vertically suspended pendulum. Okay. Laminar rods show that the period of time of each oscillation is 2 pi square root of 8 over root L root 2L over 5G. Now, the center of gravity, guys, okay? G over root 2L. Alright, that's perfect. What could be potentially very hazardous in a question like this is the center of gravity of the system. Would you agree with that? For example, I have a square lamina, like so. And what I decide to do is I only put one bar on it. The center of gravity is usually here. What happens then? Where does the center of gravity get shifted to? To a different point, probably further to the right. What's the great thing about this question? When you have all 4 bars in place, symmetrical, they almost cancel each other out, don't they? The top bar, the top way cancels the bottom way. It's like a weighing scales. Put 5 grams on the left, put 5 grams on the right. Your scale is still balanced, okay? So therefore, we only have to worry about the initial, what would have been the center of gravity in the first place. So it's L across L up, Pythagoras' theorem, root 2 L. Everybody cool with that? That's the center of gravity, and that's the P axis spinning. Now, I ends up to be root I over mgh. Just for everybody ever from now on, please specify m before you decide to enter anything into the formula. What is the m of the system? 2 pi, yes it is. And read your formulas properly. Now, what is the m of the system? I think there's 4 rods each of mass m, and the square was also of mass m, mass 5m. So 2 pi, what's I this time again? 16 ml squared. That's 5m, not m. That's a g. And my h value is root 2l. M, L, L. I think it's going to be 16 over... Oh yeah, they convert the, see the 16 and the root 2? Divide one of them by the other and you'll get 8 root 2 in the middle. So, or underneath, so 8 root 2 L all over 5G square root it. Everybody right with that? QED. So